Hi, my name is Laurie Milliken. This lecture is about measures of association. The first statistical technique we will talk about to quantify an association between variables is called a correlation. This is a technique that is used to describe the relationship between two sets of scores. A correlation coefficient is abbreviated with a lowercase r. Sometimes people use an uppercase r as well. One thing you should know from measures of association is that you cannot infer a cause and effect relationship just because two variables happen to be highly related. To infer or to prove cause and effect, you must have an experimental research design in a study where the researcher applies some kind of intervention and measures what happens as a result. Only then can you infer cause and effect. So just because two variables are highly related does not necessarily mean that one is the cause of the other. So correlation coefficients, these lowercase r's, are numbers between 0 and 1. A 1.0 is a perfectly strong relationship. A 0 means there's no relationship. So the closer to 1, the stronger the relationship. However, these correlations can have positive and negative signs. The positive or negative sign doesn't say anything about the strength of the relationship. It just tells you what direction the relationship is in. So for the two variables, if the r is positive, these two variables are related directly, meaning a higher score on one variable relates to a higher score on the other, and vice versa. A negative number is an inverse relationship, meaning a high score on one variable is related to a low score on the other, and vice versa. So that positive or negative sign only indicates direction, does not indicate strength. And so when you look at a correlation coefficient and if you're trying to determine the strength of that relationship, you need to ignore the positive or negative sign. So if you have two correlations, one is 0.8 and the other is negative 0.8, just ignore the sign, put your finger right over that negative sign and just look at the actual value of the correlation to determine strength. The only thing the negative sign tells you is that it is an inverse relationship. Generally speaking, this is how we interpret correlations. Low correlations tend to be in the 0.2s and 0.3s. High correlations tend to be in the 0.6s, 0.7s, 0.8s, and above. So in this picture, there are a bunch of hypothetical variables that are plotted. Let's just focus on a couple of them. So these scatter plots have a bunch of dots on the graph, and there is some variable on the x-axis, which is the horizontal axis, and there's another variable on the y-axis, the vertical. And so every dot on each of these scatter plots represents a person's measurement for the x variable and the y variable. And so the scatter plot that I have the circle around shows a very close clustering and a very definitive line that goes from lower left to upper right on that graph. That correlation is about a 0.96. Okay, so the scores on the x-axis, as people score higher and higher on the x, they also tend to score higher and higher on the y. Inverse, or the opposite of that, people who score lower on the x also tend to score lower on the y. Now we can contrast that with another picture, maybe this one on the lower left-hand side here, where the dots are really kind of scattered. They're not giving you any sort of pattern here. And so as people score higher and higher on the horizontal axis, they might score low on the y or high on the y. The relationship is very difficult to define. Another way to look at this is if you had to put an average line through that data to represent the average relationship between x and y, where would you put it? In this case, it's very difficult to figure out where that line would go. And there's a reason for that, because there is really no relationship here. The r, or the correlation, is very low. It's 0.025. And so that's a very low correlation compared to the other case where we had a very strong correlation. Now that correlation of 0.96 that we just saw a moment ago, that is a positive relationship. And so a high score on x relates to a high score on y. Now if we had an example of a negative correlation, the line would go in the opposite direction. It would start in the upper left-hand corner and move down to the lower right-hand corner, meaning a high score on x relates to a low score on y. and that would be an example of a negative relationship. So the correlation that we use most often is the Pearson product moment correlation. Most of our data that we make measurements with are interval or ratio scales of measurement, which I'll talk about in just a second. But when you have this type of data, you use a Pearson product moment correlation. It is a big, nasty looking equation. We will not calculate this in our class. It's very easy to have statistical software packages calculate this for you. But let me just walk you through a couple of features of this particular formula. First of all, the abbreviation N stands for the number of observations, or the number of people that are measured. And this is a very common abbreviation in statistics. You'll see it everywhere. You'll see it in research articles. So you really need to know what N stands for. N is the number of people. This other symbol, you may recognize it from back with how to calculate a mean or how to calculate a standard deviation. This funny looking E stands for sum of. And in this case, sum of stands for the sum of the x times the y measurement. So you have to remember that a correlation gives you the relationship between two variables, an x and a y. So every person in the data set has a measurement or a score for one variable and a score for another variable. Let's say I'm looking at the correlation between the number of grams of fat in my diet and my blood cholesterol scores. Well, every person in that particular study is going to have a number in the data set for the number of grams, average number of grams of fat in their diet, and another score for their blood cholesterol levels. And you can compare those two values. And so every person has an x and a y. And so x and y appears in this particular formula. It's really beyond the scope of this class to talk about how this formula was developed. Clearly someone with way too much time on their hands came up with this. But you can see the presence of x and y in this particular formula in the numerator, and then in the denominator there are two separate phrases here, both underneath a square root. One is for x and one is for y. And those two phrases relate to the variability of x and y. Anyway, so this is a very complex equation. This is what the computer software uses to calculate an R, and this tells you, it quantifies the level of a relationship between the two variables. One is x and one is y. So these scales of measurement, I mentioned them a little bit in the material from a previous week. There are several scales of measurement. So numbers can represent different kinds of things, and so a nominal scale of measurement is where the numbers actually represent categories. So sometimes researchers will code their data. I'm going to give a number 1 to all the males, and I'm going to give a 0 to all the females. So you can code your data that way. Sometimes they use that for ethnicities, and depending on the purpose of what that researcher is trying to do, you can set up numbers to represent categories for a number of different kinds of things. The next scale of measurement is ordinal. This is where the number represents a rank order of measurements. So you can imagine that in a road race, people who cross the finish line first, second, third, fourth, those numbers represent an order. And so you can take data and represent it as rank order if you want to. And when you do that, that's an ordinal scale of measurement. Really the most common scales of measurement are interval and ratio. These are continuous numbers. They typically have decimal places with them. The only difference between interval and ratio is the presence of a true 0 point. And so an interval scale of measurement, a nice example of this is temperature. There is no true 0 point, meaning that a temperature of 0 outside doesn't mean the absence of temperature. It's just another point on the scale. And in fact, a 0 Fahrenheit and a 0 Celsius are really two different numbers. And so that's an interval scale of measurement. Ratio, on the other hand, has an absolute 0 point. And so if you measure a height of 0, that means there is no height. Or a weight of 0, there is no weight. Or you measure a blood pressure of 0, there is no blood pressure. Okay, so that scale of measurement has an absolute 0 point. And for both interval and ratio, the numbers represent equal units between the measurements. So if you go from 10 to 20, the difference between 10 and 20 is the same difference as between 50 and 60. Whereas in ordinal scales, first, second, third place, the first person who crosses the finish line of a road race may cross 10 seconds ahead of the next person, who might cross 2 minutes ahead of the next person after that. So first, second, third place does not represent equal units between those numbers. So when you have these other scales of measurement, there are a bunch of different other kinds of correlations that you can run when you have different kinds of data. So the one that I already showed you, the big fancy equation, the Pearson product moment correlation, that is used for interval and ratio data. And these that you see on your screen are for different kinds of data. So you see there's some for rank order, there are some for when variables represent two categories, or when one represents some categories and the other represents continuous numbers, etc. So if you have different types of data, there are different kinds of correlations, and they're just different formulas that you can use on those types of data. Just want you to be aware of these. So something else that's important is something called the coefficient of determination. So when you pick up a research article, you might see people reporting correlations, these are the R's, or you might see people taking that R, squaring it, and expressing it as a percent. Technically that's called the coefficient of determination, although most people don't refer to it as that, they just call it the R squared. So the R squared is a number that you will see out in the literature. It's used quite a bit, and there are some advantages to using the R squared compared to just the R. So what is this R squared? So the R squared tells you the variance that is common between variables, or the proportion of variability or variance that can be accounted for in one variable by the other. And I'm sure that means nothing to you, so we're going to work on practicing this a little bit so you understand these two statements that I just read. So we'll get to that in a second. So if the R squared is high, the two variables tend to be affected by common factors. And we'll go through some examples coming up. The advantage of an R squared is that an R squared can be directly compared to another R squared, whereas an R cannot be directly compared to another R. So for example, if you have an R of 0.8 and an R of 0.4, the 0.8 is not 2 times the strength of a 0.4. You can't compare those numbers that way. What you have to do is you have to take those numbers and square them, and then compare them. So you take the 0.8 and square it, and it becomes a 0.64. You take the 0.4 and square it, and it becomes a 0.16. And so the reality is that the 0.64 is 4 times stronger than the 0.16. Okay, and that's a very different scenario than if you were to just try to compare the R's directly. You can't do that. So there is a reason why, mathematically speaking, you cannot make that comparison. You have to square these things first. And what happens is you'll see people reporting R squareds in the literature, and they will do some things with the R squareds, like sometimes they will subtract them, they will add them, and so you can do those kinds of mathematical manipulations with an R squared, and you can't do that with an R. So the R cannot be directly compared to another R, but the R squared can. So what you do is you take your R's and you square them so you can do that comparison. And you'll start getting the hang of this as we go through some articles throughout the scope of this course. So here's an example. This is some real data that I was involved in collecting. We were measuring some children who were involved in a strength training program at a local YMCA. And so these kids, let's see, how many kids? Count the dots on this graph, and that will be how many kids were in the study. Looks like there are about 12 of them. So there are 12 children who were measured. We measured how strong their legs were. We measured their leg press strength. This is on one particular machine, which is the leg press. And then we made note of their age. And so what we wanted to see was whether age and leg press strength was related. And we had the computer put a line of best fit through the data. And so that's what that diagonal line is. And what we found was that these two variables are related. The kids who tended to be older tended to be stronger. The kids who were younger tended to be a little weaker. It wasn't a perfect relationship. Not every dot fell exactly on that line, but on the average, that's what the relationship was. And you can see in the upper left-hand part of the screen, the R squared is reported. So the R squared came out to be about 0.4639. If you express that as a percent, it's 46.39%. So let's talk about what that actually means. So first of all, I want you to make a note that the y-axis, the y variable, the leg press strength, the scores for that variable ranged from somewhere around in the 70s, if you look at that, the very lowest dot, and just read where that hits the y-axis. So I don't know, 70, 75, somewhere around there. And then you take the strongest child and look to see what the value was for leg press strength for the strongest child, and that was, looks like, around 225. So there is some variability in leg press strength. It ranged from 75 up to 225. What can account for the varying scores on leg press strength? Well, one thing we can look at is age, and that's what this particular graph shows. Age can account for about 46% or 46.39% of the variability in leg press strength. And as it stands, before we'd make other measurements, the remaining percent variability is unaccounted for. So if you think about all of the things that might influence, contribute to someone's leg strength, especially children, it could be age, because as they get older, hormones start changing. Maybe training history, maybe gender, that would be a good one to look at. Maybe some kind of a genetic marker, maybe something in their nutrition. So a lot of things might account for the varying scores for leg press strength. One of those things is age, and in this particular analysis, age accounted for 46% of the leg press strength scores. Now this is very important to realize. That R squared of 0.4639, if you take that 0.4639, tap it into your calculator, and press the square root button, you will get the R. So an R squared, if you want to undo the R squared, you take that number, expressed as a decimal, and you square root it, and then that gets you back to the R. If you have an R and you want to square it, well, you just multiply it by itself, and you get the R squared. So you can go back and forth between R and R squared, and you might be asked to do that on some of the quizzes in this class. So another measure of association is something called regression. And you can have a simple regression or a multiple regression. A simple regression is a method used to determine the relationship between just two variables, an x and a y, and you'll see that regression and correlation are redundant techniques. They are, for all intents and purposes, the same kind of technique. Regression, however, allows you to be able to add more variables to do multiple regression. And so regression analysis can be used to compare variables, but also you can use it to predict one variable from another. And so we'll see another example of this as we go along. So this simple regression is identical to that Pearson product moment correlation. The R, or the R value that you get from regression, is the same that you get for the correlation. It's interpreted the same way. 0 is no relationship, 1.0 is a perfectly strong relationship, and the positive and negative sign shows direction. And so that's the same thing as correlation. Multiple regression allows you to add in more x variables. So you can see how many x variables compared to one y, and that's an advantage to using regression over correlation. So when you run a regression analysis using your statistical software, the computer creates a line of best fit, and that's the diagonal line that we looked at in that graph of age versus leg press strength. When you do a regression analysis, in addition to the R, you also get this line of best fit, and you get the amount of error around the line. It's called the standard error of estimate. So this line of best fit is y equals mx plus b. This is the equation for a straight line, you probably can remember this from maybe high school algebra or maybe college algebra. So y equals mx plus b. M is the slope of the line, how steep or how flat that line is. B is where that line intersects the y-axis, the y-intercept. X is the variable on the horizontal axis, also called the independent variable. And the y is the variable on the vertical axis, also called the dependent variable. One way to remember this is that the y variable depends on the values of x. So when x's get plugged into the equation, you plug through the math and you get a y, and that y depends on what the x's were that you put in. So from a regression we get an r. We can square it and get an r squared of this regression model. That r is the same thing as a correlation coefficient. When you have a multiple regression, you have multiple x's contributing to that r. You can get this line of best fit. So you get the actual equation for the line. And if an x and a y are highly related, you can use a measurement of x to predict what someone's y would be. And this is actually used quite a bit in medicine. So here's an easy example. You always want to have a simple way to measure whether someone might have a disease. And so let's just think about cancer. There are various markers that you measure to see if someone has cancer. For prostate cancer, there is something in the blood that you can measure to see if someone likely has prostate cancer. Well, the gold standard for determining if someone has cancer is either maybe some fancy scan that costs a lot of money, or sometimes a biopsy that would cost a lot of money. You don't want to be doing these scans or biopsies on just anyone that you suspect might have cancer. You definitely don't want to use that as a screening tool. And so what people in medicine have looked for is something, a screening tool that's easy to use, that's low cost, that might do a pretty good job of identifying people who might have a disease. Well, when they come up with those screening tools, what they do is they take something that they think might do a pretty good job of determining who has the disease, and they compare it to that gold standard, the biopsy, the scan. And so in the study that they use to establish the effectiveness of that screening tool, they take a group of people and they measure the new easy thing that they're trying to validate, and they measure whether the group of people actually has the disease or not by using a fancy, expensive technique. And then what they do is they plot it on a graph and they do regression. And so the x variable is that new screening tool, and it gets compared to the y. And the y is the score or the result of that high-tech tool. And so what you get is this line of best fit, and you can take someone's score from their x variable, plug it into the equation, and predict what the outcome is in the y. So you can compare these two measures of disease. And so if an x variable does a pretty good job predicting the y, then you can use the x to replace the y in practice. And so everyone doesn't need to go out and have the big, fancy, expensive test. They can do a screening test. And so there are lots of cases where very simple tests have been developed and validated compared against a gold standard source. Anyway, the R from the regression, the line of best fit, and the standard error of estimate is important in those kinds of studies. And so if you're trying to measure an x variable and predict what the y might be, the standard error of estimate gives you the error rate of that estimate. So it's almost like the standard deviation of the line of best fit. And so we'll talk about this a little bit more in a second. But if you are estimating a y variable from someone's x based on a previously determined regression equation, that estimate of y is accurate plus or minus the standard error of estimate. So this is important, the standard error of estimate. If you take an x value that you measure in someone, and then then plug it into the line of best fit equation that was previously developed, and you predict what their y must be, that prediction is accurate, plus or minus the standard error of estimate. Okay. The other thing you get is this, well, it's actually part of the line of best fit, it's the slope. The slope for that x, and if you have many x's in the equation, as in a multiple regression equation, you have many slopes. And so in the research literature, you will often see the term beta coefficient. And the beta coefficient is another word for slope. So sometimes you'll see people reporting a beta coefficient. And so beta coefficients can be positive or negative, and it shows the direction of the relationship. X is related to y positively when the slope is positive, and x is related to y negatively when the slope for x is negative. And so a slope's positive or negative sign shows the direction of the association between x, that x and y. That slope also depends on the unit of measure of x. And so we'll see that in an example I have coming up. And so the size of the slope depends on whether x was measured in inches or centimeters, etc. But you can actually standardize the beta coefficient so that you can look to see in any given regression equation how much weight one variable carries compared to another. And so once you standardize and account for the different units of measure of all of the x variables in the equation, you can compare one to another to see which one carries the most weight. The bigger the standardized the standardized beta coefficient, the more weight it carries in the equation. So here is our relationship again between age and leg press strength. Just a reminder, the age variable accounted for about 46% of the variability in leg press strength. Now if we wanted to, we could turn this very simple regression into a multiple regression by adding in more x's. And so if age accounts for 46%, if we add another variable to this analysis, we could see if that r squared goes up. So maybe we can add gender. Maybe gender accounts for some variability in leg press strength. Maybe training status. If someone does a lot of strength training, that would improve or account for more variability in leg press strength. So just to show you the aspect of this regression equation, you can see it's written in the upper left-hand corner. Y equals 16.901 times x minus 25.98. That is y equals mx plus b. The m, the slope, is the 16.901, and the y-intercept is the negative 25.98. And so I took a red line and I extended that line of best fit so you could see that indeed that line of best fit crosses the y-axis in the negative side, so it actually crosses exactly at 25.98. And then the steepness or the flatness of that line is the slope, rise over run, the change in y over the change in x. So for every one increment on the x-axis, so for every 1 year increase in age, there's approximately a 16.901 increase in leg press strength. So let me say that again. For every one increment on the x-axis, age, for every one increment increase in age, there is approximately a 16.901 increase in leg press strength. That's 16.901 pounds increase in leg press strength. Okay, so that is that line of best fit. Now, if we wanted to be able to predict what a child's strength might be based on age alone, we could do that. We could take that y equals mx plus b, we could measure someone's age. Okay, so I have a 10-year-old child. I'll plug 10 into where x is sitting, 10 times 16.901 minus 25.98, hit your equals button, you will get a prediction of what that y will be. So a 10-year-old will have a leg press strength that is predicted to be about what? Well, take the 10 substitute it in for x in the equation, multiply it by the 16.901, subtract the y-intercept of negative 25.98, and you get a prediction of strength. Now, if I told you that the standard error of estimate is 17 pounds, that means that the predicted y for that 10-year-old is accurate plus or minus 17 pounds. And that 17 pounds, that's the standard error of estimate. That is generated along with this regression analysis. It tells you the prediction error. And that prediction error will be smaller if the points are more clustered around that line of best fit. The prediction error will be bigger if the dots are scattered further away from that line of best fit. So the standard error of estimate is almost like the standard deviation of the line of best fit. And what I've tried to do is I've tried to put a little normal curve right on that line of best fit, with the mean of the normal curve being the regression line. And so there's variability around the regression line. The further away the points are scattered, the higher the standard error of estimate, the worse the prediction. The more clustered the points are along the line, you'll get a smaller standard error of estimate, and then you'll have a more accurate prediction of y. So just to review again, simple and multiple regression. Simple regression just has one x variable, one x compared to one y. And then a multiple regression actually can have many x's. So in this particular example, there is one x, x sub 1, the first x variable, with its slope, m sub 1. There is another x variable, a second one, with its slope. And then there's another x variable, number 3, with its slope. On, and then there's one y-intercept, which is b. And so you can have many x's in a regression analysis. Here is a real-world example of a multiple regression equation. So there is a way that you can predict or estimate how many calories you burn at rest. So this is called your basal metabolic rate. And so there's an equation for men and an equation for women. And they're listed on the screen. So if you want to calculate about how many calories you burn at rest, you can just plug your information for weight, height, and age into the equation and plug through the math, and you would have an estimate of how many calories you burn at rest. There's one for men, one for women. Now this is both of these are multiple regression equations. So let me just show you. Let's just look at the equation for men. The 66, that's the y-intercept. The 13.7 is the slope associated with the first x variable, weight, measured in kilograms. The next x variable is height, with its slope of 5. The next x variable is age in years, with its slope a negative 6.8. So you have mx, mx, mx. You have a slope in an x variable. You have one y-intercept. All of this equals a y, in this case is basal metabolic rate. And so if you picture this, this prediction, you can take three things, weight, height, and age, substitute your numbers in for each x variable, multiply each x by its slope, and then get a prediction of your basal metabolic rate. If we had the standard error of estimate with each of these equations, you would know how accurate that prediction is. It would be plus or minus a certain number, which is the standard error of estimate. I want you to realize something, though, that the slope for weight and the slope for height are both positive numbers for both the male equation and the female equation. The slope for age is a negative number. So this means that weight and height are positively related to basal metabolic rate. The taller you are and the heavier you weigh, the higher number of calories you burn at rest. Whereas age, as you get older, your basal metabolic rate decreases. A higher age is related to a lower basal metabolic rate. And so just by looking at the numbers in this equation, you can pick out the slope and each x variable, you can pick out the y-intercept, and you can see if these slopes are positive slopes or negative slopes. Now, what's not on this particular slide is, like I said, the standard error of estimate for each of these equations. So how accurate are these predictions? Age, height, weight, predicting basal metabolic rate. How accurate? Well, if they reported the standard error of estimate, which they should if you go back to this original paper, you would know how accurate these estimates are. The other thing that's not on here is the correlation, the R. How well do age, weight, and height relate to basal metabolic rate? And you have to have a strong relationship for weight, height, and age to replace a direct measurement of basal metabolic rate. So basal metabolic rate is actually really tough to measure. You have to go into the lab. They need specialized equipment. You have to go in under certain conditions, fasting, and you have to relax. It takes a long time to measure this. You have to have specialized equipment. So it's a big deal to actually directly measure basal metabolic rate. And so people were looking for an easy way to replace that measurement. And they found that weight, height, and age together predicted basal metabolic rate pretty well. And so those three X variables related to the Y pretty strongly. And those three could be used to replace the direct measurement of basal metabolic rate. So in summary, we've been talking about the R and the R squared, which are numbers that help us quantify the strength of a relationship between two variables or sometimes many X's and a Y. Regression equations have an X and a Y variable. X's are the independent variables and the Y is the dependent. Each X has a slope. If there are many X's, it is a multiple regression equation. If there's just one X, it's a simple regression equation. And of course, for any line of best fit or any equation for a line, you need a y-intercept as well. When you do regression analyses, or most likely you have the computer do them for you, you get the R, you get the line of best fit, and you get this standard error of estimate. If you wanted to use the X's to predict the Y, how accurate would those predictions be? That's given to you by the standard error of estimate. And I've already talked about simple versus multiple regression. So as you go through reading some of the content, we will start looking at some articles and looking at how people present the either correlation or regression results in research articles. So hopefully you'll start getting the hang of interpreting some of those results. Also, there are some examples of how to calculate these things. If you're interested, posted on the website. You will not have to calculate any of these by hand in this course. There are computer software packages that are much more adept at that. But if you are interested and want to see how it's calculated, I've given you some examples of that online. The last thing I want to talk about is this p-value. We've talked about it earlier in this course already. The p-value is the level of statistical significance. And you will see p-values reported along with the results from correlations and regressions. So the R or the R squared can be statistically significant or not. Also, you can look at the statistical significance of each X variable in an equation. So sometimes you can have many X's in a regression equation being compared to one Y, and some of the X's are significantly related and other X's are not. And so you can have a p-value with each X variable. And so you'll see p-values reported that coincide with the R or the R squared, and you'll see p-values reported with each individual X variable in an equation as well. So you'll see those p-values out there in the research articles as well.